Okay, I guess we'll start then. Okay, so I'm Andy Tomlin. I'm going to be talking to you about key value SSDs. So I think everyone here is familiar with this problem that all our legacy storage uses fixed size containers, LBAs, or in the FTL on the devices, a mapping unit of 4K. And real objects don't fit into these fixed size containers because real objects aren't a fixed size. And so what we've done over the years is we've added mapping layers in the host to solve this problem. And this mapping is a source of a lot of complexity and performance and scaling issues. And all this results in a lot of over-provisioning of the flash and the servers as the only solution at the moment. So let's just first think about why do drives wear out and need replacement. And you know, a lot of systems today are storing fairly small objects. If you think about a lot of the social media applications or messaging applications, these are very small objects. And the problem is when you have a fixed size container with a small object and you only want to change one tiny little object in that container, potentially you rewrite all the other objects, even though they didn't change. To change my red ball to a yellow ball, I rewrote all the other balls. And this results in a lot of wear and a lot of power. So today's layered architecture is highly inefficient. So we're all familiar with these layers where we have a mapping system in the SSD and multiple 1, 2, or 3 additional mapping layers in the device, be that host file systems, databases, whatever. There's a lot of additional mapping systems. Now, these layers add a significant amount of host software and management complexity. And the important point here is these layers aren't additive, they multiply. And these layers in the host, they require a lot of CPU power. So, you know, typically about 2 cores per drive is spent in managing the garbage collection on these devices. And as a result, the drives wear faster, they're burning power and impacting performance. So effectively, we're on this like this treadmill where we're running very fast to move at actually a slower rate. And this complexity creates all kinds of problems. We're familiar with things like noisy neighbors and all these types of issues. These are all down to this, we're running very fast just to do something very simple. So the existing architecture cannot scale to meet the growing needs. So let's look at what a typical legacy block stacks today. And this is actually a fairly simple one. So here what I'm showing is we've got a flash management system on the SSD. And that flash management system has, as do all these mapping systems, they have several fundamental attributes. The first one is they allocate space. The second one is they track location information via metadata. And thirdly, they do garbage collection. So all mapping systems in some form do all these elements. That's what makes them a mapping system. And all these layers are independent of each other. And as we said before, because of that, these layers multiply. So even if I'm only storing metadata for this file system, it's consuming space and metadata on the device. So these layers all stack up, both from a garbage collection standpoint and in metadata. We have metadata for metadata. So one of the new trends is ZNS. And when I say ZNS, I want to include into that all data placement technologies. So ZNS is not the only idea out there. There's several others, and they're all variants on the same idea. And the idea is, let's solve the legacy map stacking problem by just moving everything to the host. Okay, that's the premise of data placement. You know, the device we can't avoid this 2 levels of problems or 3 or 4 levels. So let's just keep the device as simple as possible, and let's just move all the problem of garbage collection onto the host. Now, it's a good idea, and you know, the idea here is that we can have less metadata in the device and less garbage collection, and we'll simplify the device flash management, and we'll just write in very big chunks and arrays in very big chunks. And in terms of being better than the legacy solution, is absolutely better. And the idea is, by doing this very large writes and very large arrays, we'll kind of neutralize the device GC. We'll pretend it doesn't exist. And we'll do that by doing these very big writes and very big arrays. We'll make the garbage collection trivial on the device. And that's the idea. And again, I think it's better than the legacy solution. But there's an issue with this. And the issue is, this model is based on a very simple model of the flash, that basically on the device it's just a write pointer, the blocks are all uniform size, and I don't have to have a complicated model of the flash. However, this model doesn't actually match reality. Reality is, on the device, a lot more complicated than this simple model. We have variable size ECC, which means we have variable size blocks, there's defects, there's read disturb, there's wear. All these device level issues are actually a lot more complicated than the ZNS model. It's a good abstraction, but it doesn't reflect reality. So what we have here is we're still going to have an SSD mapping system with over-provisioning, metadata, and garbage collection. We're going to hope it's less. And my analogy here is this ZNS scheme, or data placement in general, is really the idea of balancing a broom on your hand. And we all know you can balance a broom on your hand for quite a long time if you're, well, at least we could when we were young. You can do that for quite successfully, okay? It's great. However, it's dynamically stable, but it's not inherently stable. And so eventually these problems here will bite you. So my premise here is, yes, ZNS improves on the legacy stack, but the flip side of this pro, which is a good pro, is it's pulling all the device complexity into the host. Now, storage history has told us that we've done this before. Remember cylinder head sectors on disk drives, and even controllers that actually controlled the HDD. This idea that somehow pulling device complexity into the host so the host can manage it, we've tried this before. It's not been successful in the past. Maybe we'll do a better job, but the problem here is really that the interface abstraction does not match the needs of the application. Applications want to not worry about where things are. They want to store a thing. That thing is a variable size.
Well, actually, what you said is that the abstraction doesn't match the device either. It's not just it doesn't match the application, it doesn't match the real device. It's too abstract.
Yes.
Which is another problem that's not even listed, I guess. I mean, that seems like a different problem, an additional problem from what you have.
Yeah, I mean, the simple block interface that the device exposes to the host doesn't match any real-world usages that the host actually wants to make of the storage. And the other, so the interface abstraction doesn't match, and we get poor scaling. Now you've moved all this workload that you previously were doing on the device, now you're doing it on the host. That doesn't scale well, and requires the host to be well behaved. So my contention here is fix the abstraction, stop trying to balance the broom, and make sure that with the KV SSD, we can put all the over-provisioning in one place, the device, axiomatically the best solution. So a key value SSD solves this fundamental problem. It removes the need for the host to track the data location. That one thing, if I don't need to track the location, I don't need to allocate, I don't need to do garbage collection, I don't need to have any metadata on where I kept stuff. So these mapping layers are now eliminated, not minimized, eliminated. So again, this is axiomatic the optimal solution. You can't do better than this. It's going to be less power, higher performance, better scaling, and when you come to some of the problems that they have in the databases and the application space, you no longer need to optimize. So all that optimization that you previously had to do, it goes away. This will ultimately lower CapEx and OpEx. So let's just, again, look at this from a slightly different angle. So we're familiar with the legacy solution here, where we have mapping systems on both the host and the device. And here, these boxes in yellow, these are where the issue is, because the host and the device are all doing their own thing, there's no coordination, and they multiply together. So if you look, the allocation and tracking of the value location in the legacy solution is done on the host. The host is garbage collecting its logical space. The device is garbage collection its flash space. If you want to do compression, you have to do that on the host. And then if you look at something like LSM, the log structure merge, this is an application write amplification in the 10 to 30x range. Now, this gets multiplied by the device write amplification, which is about 3. So now we end up with a 30 to 90 write amplification. So ZNS says, okay, let's solve this problem by just moving everything onto the host. So now we're going to say the host is going to also now garbage collect the flash space, mostly, because again, remember, the abstraction doesn't quite match. And so now we end up with a much better flash write amplification, but we didn't solve the application write amplification. That also went up a little bit, because now you're having to do a little bit, few extra things that you didn't have to do before. So yes, we've taken a 30 to 90 write amplification down to a 13 to 33, so that's great. But look now, I've now got to, the host CPU's got to perform data placement, GC, compression, metadata management. So 95% of the host bandwidth and CPU is now doing all this work that previously, well, was doing a lot of that work before with the legacy solution, but only a small fraction of the CPU is left for application functionality. And that's how we've been working for a long time. We just keep throwing more hardware at the problem. But that doesn't really solve the long-term problem. And so the opposite direction is instead of the host taking a responsibility for this, let's move that complexity onto the device. So now, instead of going to here with all this is on the host, we're now saying all this is on the device. The device obviously can do compression in hardware. If you can figure out how to make one of these work, it has excellent properties. And now the host CPU is 100% dedicated to application functionality. And the other interesting byproduct of this, which hopefully is obvious, this now scales with the devices. If you want it to go faster, add more devices. We know how to do that. So this will always be a lower power solution, and it also lowers the overall write amplification. That's going to mean things like QLC might actually work in anything other than a very trivial application.
What's the source of numbers in the table and under the table?
So these application numbers have come from studies that you can find on the internet of people who've done experiments with, mainly with RocksDB. So these numbers here are from analysis of our technology. These numbers here came from some papers by Kioxia and others. I don't actually have the citations available. CPU utilizations, these are somewhat estimates, but they come from, if you look at actually the write amplification, and we know that experimentally that it's about 2 cores per device. That's from practical experience. If you look at what the ratio of workload that is, that's where the 95 is actually probably conservative.
How much is that the compression? Are you assuming that's software compression?
Yes. If you want to ask, I can follow up with you later if you want to find out. So let's look at compute scaling. So, and why I think data placement is ultimately going to be a dead end. So we're past the frequency era. We're no longer really scaling our compute capability by increasing frequency. There's always some amount of frequency increase, but we've kind of flattened out. And similarly with cores, we're pretty much at the end of the adding cores. We now have CPUs with 128 cores. It's not going to scale. We're not going to scale our platforms by adding more cores at this point. So today, we're really in the era of the smart hardware offloads. And some of these are pretty obvious. GPU, so a lot of machine learning algorithms are moving onto the GPU. We have smart NICs. We have custom security instructions. We have FPGAs. We're seeing more and more FPGAs going into data centers. These are all technologies that we're trying to do custom hardware that's programmable to allow us to offload things that we previously just did in the CPU. And the problem is, these data placement technologies, these are going in the opposite direction. They're saying, let's pull workload off the device and pull it into the host. And that is going to result in scaling problems. And the other issue is, as I've talked to some customers, ZNS is viewed as very complicated, and that data placement code is hard to write. And it's really only going to be a solution for the top 3 or 4 cloud providers. I don't think it's going to really be popular into many actual in on-prem or other solutions. Now, for the cloud providers, it's good. I mean, I'm not against ZNS. I still think it's better than the alternative, but I don't think it's has as high a potential as a KV SSD. So the other thing we were talking about is how do we offload, and we're talking about, I've sat through several presentations today on computational storage. How do we offload workload from the host to the device? Well, my belief here is that if you're going to offload workload from the host to the storage device, probably the best thing to offload is the storage workload. So customers today have an optimization problem. And right now, they have a very complicated world. They have a hardware platform where they have to figure out instance types, storage types, all these hardware issues they have to work with. They have OS management they have to do, and database where they're worrying about how their caching and indexing works. The practical upshot of all this is most database solutions today don't run optimized. They just get put together and they work how they work. And the vast majority of platforms work this way. So, because now, obviously, when you have a problem, you have to apply your engineer now to try and figure out, well, what's the problem, and maybe we can optimize something. And that's kind of, it's done on an exception basis. And this is very expensive for customers, and also often these optimizations may be short-lived. You may optimize and then your application changes, and before you know it, it's no longer actually optimized. So with a KV SSD, there's less hardware, the device has linear scaling, and this smaller software stack eliminates a lot of these optimization problems. So let's talk a little bit about metadata, because this is the key problem. Key, literally. So the key size that you need in a key value store is driven by the number of objects that you're storing. Not the size of the object, but the number. And you need enough bits that the collision probability is manageable. And manageable, obviously, is subject to interpretation on different designs, but fundamentally, the collisions is based on the birthday paradox. I'm not going to go into the explanation of that. There's plenty of stuff on Wikipedia to explain about the birthday problem, or the birthday paradox. But let's just look at a couple of examples. So here we have a 16 terabyte data size. And let's look at two different average object size. So if I have 128 byte average object size, then I have 2 to the 37 objects. And for 2 to the 37 objects, it works out, you do the math, you need about 104 bits. And with 104 bits, that you would get approximately 64 collisions with that capacity and object size. And similarly, the numbers, obviously, when you go to a larger object size, you have less objects. Theoretically, you can get away with a smaller key. And you can see, though, the math continues. So you get a large drive with small objects. You need a very, very large key. So this key size and the number of keys is what drives the metadata size. So the same examples here show how the metadata size. So theoretically, if I have a 16 terabyte drive with 128 byte object size times the number of objects, you end up with a metadata size of 2.8 terabytes. So I have 16 terabytes of data, but I have 2.5 terabytes of metadata. So it's what, 20%? Close. Now, compare that to a legacy drive, my 18 terabyte drive without compression, it was 0.016 terabytes of metadata. So you can see this number here is very large compared to this here. And that's the key problem in building a key value SSD. That what we're seeing here is between a legacy drive with and without compression and a key value drive, we have 2 to 3 orders of magnitude more metadata. Look here, this configuration here, it's a massive amount of metadata. So the implication of this is if you're building a key value SSD, you must build a native key value SSD. You can't build a layered approach. So you can't just say, okay, well, we're going to build a key value SSD, we're just going to port LSM into the device, and we'll run LSM in the device, and that's going to work. It won't. Because of the scales here. So I also made the claim that the power is much reduced. So why is that? Well, there's two parts to power. Power basically is the power per operation and the number of operations. So if you think about a garbage collection, and obviously the system is dominated by the garbage collection. The garbage collection has three main pieces. The first one is identify what to garbage collection. So that means you must be tracking metadata that enables you to identify which area you want to garbage collect, or is the optimum. Then you have to have a process to determine what data is valid, because obviously your garbage collection to compact data together, and you have to figure out which pieces are valid, which pieces aren't, and finally you have to copy the valid data. So with a host-based garbage collection, you're going to issue a command to the device will, like a read, and the read with data will come through the controller, through PCI Express bus, into DRAM. CPU is going to run a bunch of instructions, typically about in the tens of thousands of instructions per garbage collection. And then data gets written back. So this whole loop is effectively the power for one operation. Now, with device-based garbage collection, this is pretty much handled by custom hardware, and the loop is much smaller. It's just into the device and back to the flash. So this should be 1 to 2 orders of magnitude power difference, which is quite significant. And that's just the power per operation. And then we have the number of operations. So the KV SSD has significantly less operations because the overall write amplification is reduced, and either versus legacy or ZNS. And so we have less operations. Less operations with lower power per operation. It's a massive power saving. So back to why must you have a late native solution? So today, as we look at the legacy stack, this is effectively the maximum metadata and the maximum garbage collection. Now, if you try to do this layered approach, unfortunately, although it's simpler to implement, you kind of end up with the same problem, that you end up with two systems and the garbage collections and metadata multiplying together, which means the only way to make this really viable is to have a native KV. And again, the complexity here is how to deal with the metadata. So if this is so great, why isn't everybody doing it? Samsung even came out with a proof of concept, which obviously never really has not really gone anywhere yet. And the real reason why even though it's great, no one's doing it, is because, first of all, it's hard. It really requires a radical rethink and innovation on how the SSD copes with metadata. You can't just take your existing FTL and tweak it a little bit and think you're going to end up with something that works. Because we're talking 20 to 100x the amount of metadata. The software stack, the KV is completely different to legacy storage, and there's no software stack today. And then ecosystem. Customers want a simple path to a solution that solves the problem and is easy to adapt. So these are all reasons why we don't see KV today. There's nothing inherently wrong with the technology, just, it's a tough problem. I think also KV is going to enable some interesting new solutions. And there are several ideas here. I'm just going to go through one of them. And that is NVIDIA and IBM did a proof of concept where they had they offloaded the transfer of data during a machine learning actually to the GPU. So it's like a direct storage for games where the GPU is directly reading the data. And so instead of this model that we have typically today, where the CPU is managing the whole thing and then does the data transfer, instead what the CPU does is it provides all the file system information, like the offsets. You don't want to run the file system on the GPU, but basically provides a bunch of offset information, and now the GPU can pull the data in as it needs and write. But this is done through effectively the CPU interpreting the file system and providing all this information now to the GPU. Now, can you imagine what this would be like with the KV SSD? You would just tell the CPU would just tell the GPU, these are the objects you need. And it could just issue the commands. Doesn't need to worry about file system, doesn't really worry about offsets. It can just interact directly with the KV SSD, and the CPU is not involved at all beyond that initialization step. So I think that would be a very interesting application for a KV SSD. So this is what we're working on at Keystore. Our technology consists of various pieces that make up our FTL. And again, this is all about how do you manage the amount of metadata. The other thing we do is we allow mixed namespaces. So you can have, on the device, you can have a namespace that's like a legacy block-based, and you can have namespaces that are key value. So we provide that flexibility. And a lot of the work is done with some custom hardware engines to optimize all this process. And then we have our storage engine, which we're building to make RocksDB API compatible. The idea here is we want to be able to plug into applications that allow for a storage engine. It looks like currently that RocksDB is probably the best API to do that. Okay, I think that's about it. Any questions?
Is this available for purchase right now?
No.
Okay. Second question, do the keys have to be unique?
Do the keys have to be unique?
Is there one object for each key? Do you have
Yes.
So that every key, every object has a unique key.
Yes.
So what is the metadata for exactly?
Well, the metadata is the information needed to track that key. So from the host side, you say, here's my key. Please get, you may say, does it exist? Or you would say, please retrieve the key or store it, whatever. And so the metadata is the information that you need to track where that is.
What if you could determine where it is without the metadata?
Well, that would be great.
Well, I'm all
Okay. Any other questions? Sorry? That's a very interesting question. Yeah, it's a very good question. Theoretically, no. There's no reason why you would have a limit. I think our current plan is to actually limit the size to about 64K on the basis that it doesn't add a whole bunch of value to support these very large, very large keys because an object can be split up anyway by just breaking up into pieces and having lots more keys. So we're not trying to be a object storage device. We're trying to be a key value SSD. I think there's so we're probably not going to support indefinitely. In the storage engine, we'll allow that to very large objects to be stored, but it's a fairly trivial problem to store large objects. The problem actually is the smaller objects. The smaller objects are much harder than the larger objects. But there's no reason why, in fact, the standard does allow you to support, through the KV standard, you can support any size objects, but you can basically report to the host, well, this is my largest size that I support or value. And so we plan to keep that small just as a simplification.
One question. So if the object size is not aligned to the 4K or 8K, will there be any recommendation to the storage?
Well, yeah, I mean, that's the problem. By definition, objects are not 4 or 8K aligned. Objects could be 1 byte, they could be gigabytes. So each object is completely variable in size. So the system has to deal with that. You can't run this on top of a 4K block storage. You end up with a very inefficient system.
Would you like to talk about the competition?
Sure. I mean, in terms of ZNS?
Let's say in terms of Samsung, Flyops.
Sure. So Plyops, they have a card solution. In fact, in many ways similar to this. I actually hope they're very successful. I think they have an interesting solution. I think probably the key differences would be we're trying to build a KV SSD standard device. We're not trying to build a card product, even if they look very similar. It may end up being that I've never actually benchmarked the Plyops device, so I don't know exactly how they would perform in difference, but probably fairly similar in many respects.
What about
Samsung, my interpretation of what Samsung has done is they did a software layer in the device, and they've been at the forefront and innovated in this area. They've been the ones driving the standards. So I don't have strong opinions on how valid their solution is, other than it didn't really take off, and maybe that was because of the software stack. And I think the challenge here is for a company like Samsung. Samsung's a very large company. They can't do, it's very hard for large companies to innovate in this kind of area because they need to be shipping, exabytes of flash. KV SSD certainly at its beginning, is not going to be that. You know, the other problem Samsung has is who's the second source? When Samsung wants to ship, you know, exabytes of this thing, customers aren't going to buy it unless they have a second source. And so I would imagine at some point in the future they will come back to it. They have obviously they're probably behind the doors, behind the screens, still developing it. I don't know exactly what they're doing, but they may well come out with a native solution. I don't know. But I think it's inherently a new technology, and especially in storage, new technologies are hard. And big companies generally don't do very well with this type of problem set. But I really hope that PlayOps is successful in what they're doing, and they help expand the market. There's plenty of room for everybody to play. Does that answer your question? Any other questions? Okay. Thank you, everybody.